welcome to the lecture of this finite volume method. Now, if you try to do the calculation for the gradient, let us say you mark these things properly. So, we have element 9 and element 9 is sort of, if you look at that, and element 9 here, this here is the local index. So, that means I have defined 1, 2, 3, 4, 5, 6 like that. Okay. 1, 2, 3, 4, 5, 6. So, these are my 6 surrounding elements. So, here in this particular figure we stay in the local indexing, and if you go to the global indexing, so this is how your global indexing would be associated. This is my element number 9. Here this is exactly same what we are interested to calculate that, and 9 now 1, 2, 10, 11, 8, 6, these are my global indexing. So, if you compare the picture here 1, 2, 10, 11, 8, 6, this is how my global system was there, and I have transformed them to a local system and then local to global. So, this is how the connectivity is maintained. Now, if you do the calculation of the gradient for this local indexing here, so this will be 1 by Vc, okay, and I need to calculate Fs1, Sf1 plus phi F2, Sf2 plus phi F3, Sf3, phi F4, Sf4 plus phi F5, Sf5 plus phi F6, Sf6. Okay. So, that takes into account of all these surface normal vector Sf1, Sf2, Sf3, which are connected with our local indexing element, that is Sf1, Sf2, Sf3, Sf4, Sf5, Sf6, and these are my local connecting element F1, F2, F3, F4, F5, 6. Okay. So, one can write other way around, this can be equivalently written that 1 by V 0 phi 1 S1 phi 2 S2. So, that is meaning is same. So, you write in this fashion or you write in this fashion, they actually point towards the same thing. So, what typically it says, you have this local connectivity, you have this local outward normal vector, and you have 6 element which is surrounding to that particular element, and there you get all these 1, 2, 3, 4, 5, 6 normal vectors. So, your gradient calculation would be written like that. Okay. So, once you then, and if you look at the other part, you can always have this global indexing and you can write these things in a global pattern. Now, if you just concentrate on this particular element and fetch the element connectivity information. So, the element connectivity information, if you write down, then so the what are the neighbors, that is first thing. Neighbors you have two indexing, the local indexing is 1, 2, 3, 4, 5, 6, that is my local indexing. Now, the global indexing, that goes back to, this is 1, 2, 3, 4, 5, 6. So, if you look at global, this would be node number 1, this is 2, this is 10, 11, 8, 6. So, this is my global indexing. So, 1 maps to this, 2 maps to this, 3 maps to 10, 4 maps to 11, 6 maps to 6, or vice versa. The global one maps to local one, so either way is true. So, this is the local to global connectivity for the neighbors. So, that takes into account all 6 elements which are sitting there surrounding that element number 9. So, that is one. Now, you can see the faces. Okay. Similarly, like your neighboring elements, you would have the face also local connectivity and the global connectivity. So, the local connectivity, if you first write down 1, 2, 3, 4, 5, 6, this is local connectivity. Now, local face 1 is this one. So, this is mapping with number. So, this is my face 1 local mapping or the surface vector. So, this is mapping with the face of 11. So, the global is 11. 2, this is my second surface and the global surface is 10. Similarly, this is my face 3, global number of the face is 16. Face 4, global number of the face 4 is 22. Face 5, global number is 23. Face 6, global number is 15. So, that is the global indexing. So, if you see kind of information that a unstructured grid system needs to have, that is quite rigorous, because it requires these neighbors and neighboring element, then local indexing of the neighboring element should be connected with the global indexing, that is one part of it, then the faces. Now, all the faces in the complete domain are numbered. Now, for this particular element, the local faces were 1, 2, 3, 4, 5, 6, and they are connected with the global numbers 11, 10, 16, 22, 23, 15. So, this means the connectivity between local face and the global face also very important, and this is how the connectivity is stored, and in handling of the data structure one has to do that. So, that takes into account neighboring element, neighboring faces. So, what is left here? Now, the information of nodes, that means this particular element does have 6 nodes or 6 vertices, and these vertices also belong to this face or global faces, and they also belongs to the other neighboring element. So, the again if you look at it, the local nodes must be 1, 2, 3, 4, 5, 6. So, if you look at that, local nodes are 1, 2, 3, 4, 5, 6, these are local nodes. Okay. So, accordingly you can have global nodes, and the global node number one can define. So, if you say these are my local node number, you start from here 1, 2, 3, 4, 5, 6, these are local node number, and there could be some global node number x1, x2, x3, x4, x5, x6. Okay. So, these are my global node number. So, that says since that and they would be again mapped between local to global numbering. So, all this information need to be stored in my data structure. So, once we say for a unstructured grid system the element connectivity must include three things, One is the neighboring element connectivity. So, that takes into account the mapping between local indexing to global indexing, faces, that takes into account the local face to the global face, nodes, local node to global node. All these information need to be stored in your data structure before doing any calculations. Now, if we coming back to the discussion of the gradient calculation, this is what we have done in the local system. So, local system, if you do the same calculation of the global one, okay, then the global calculation would be 1 by V9, and then here if you go by one after another, phi f1 sf1, phi f1 is sitting or connected here with this. So, this essentially connected with the these things, the 16. So, what happens here, that this particular term, that if you see, this is your local term and this is your global term. So, this would be the global calculation would be connected with this face of 11, and your normal vector, that SF1, which is actually going inward. So, the sign would be negative. So, this would be phi 11 and S11. Okay. Because this is my local phi f1 S of1. If I come to the global one, my face is 11. So, the flux should be calculated at the face 11, and the normal vectors or the surface vector actually moving inwards. So, the negative sign comes in. Now, you look at to F8 S2, that is connected with the again surface 10, and the vector is pointing towards inward. So, this will have again a negative sign. If you go to F3 SF3, surface is 16, here the surface vector is going outward. So, it follows the positive sign. So, that will be like that. F4, that means it is connected with the 22, face number 22, and the surface vector is also going outward. So, this would be phi 22 is 22. Phi F5 and SF5, this is here. If you go there, surface is 23 and the vector is coming towards inside, again this will come with negative sign. And the last one is the sixth one. If you go here in the global, the face number is 15 and the vector is pointing towards inside. So, this will also come with negative sign. Okay. So, that is how you do the calculation, that local indexing you do the calculation, and then from local when you go down to global you require the information of the fluxes. So, one thing important to note here is that the this local surface vector, they not necessarily would be outward direction. So, as we have seen in this particular example, the local surface vector, when we have drawn a local system, we have assumed a standard sign convention, but when you do exact calculation, essentially for the sake of this example, we have shown some outward, some inward. So, that means the local surface vector does not mean that it is always going to be outward direction. So, it can be outward, but now point here is that if you just look at this element and look at this element number 10. So, 9 is connected with 10 through the face number 16. Now, when you look at the face number 16 for 9, the surface vector is going outward, but at the same time when you look at the element number 10 or while doing the calculation for the element number 10, you will be looking at this surface, it is pointing inward. So, this gives you a clear idea, or reversely you can think about this element number 1, which is here connected through the face 11 with 9, and the local surface vector actually going inward for this face for element number 9, but at the same time when you do the calculation for element number 1, the surface vector would be going outward. So, one case it is negative, that is coming inward, the same surface vector would be the positive for the other element which has that common face. So, that means the sign of surface vector also needs to be calculated and stored. So, that information is also required and very important. Okay. So, how one can do that? So, the let us say for sine function, one can use this kind of gradient calculation, let us say delta phi k in general divided by 1 by V k minus summation f n b k less than k, that goes towards n phi n s n plus summation f n b k greater than k goes to n phi n s n. So, this is how the equation for the gradient, can be modified. Okay. So, this will take care that sign for an individual element when it goes outward or when it comes inward. Okay. Now, so that means basically the orientation of the face, the orientation of the face, that also can be defined in a standard fashion. Okay. So, this is very important again. The orientation of the face must be defined in a standard fashion by indexing the elements in a specified order. So, by doing that you can actually store the orientation of the face, and that can be stored by doing this. Now, essentially what that does tell you, that if you have two particular element, then you need to have this orientation. One case it can go this, other case should be outward. So, one case it is owner, other case is the neighbor. So, this one can see like this: you have a owner element, you have a neighboring element, these are the center of those two elements, and this is the surface vector, and this is the face. So, the orientation needs to be accounted for, or rather stored, so that you can have proper clarity on these elements. And the similar thing, this is in 2D. So, this gives you an idea, this is 2D and this is in 3D. So, that gives you an idea about owner, neighbor and face, so that you have an idea about the orientation. And if you look at the 3D element, this is the connecting face, this is the center, this guy is the owner, this guy is the neighbor, and this is where the surface vector. So, that means if you have considered the interface between two elements, then one element it is positive. So, one case it is positive, other case it is negative. So, once you look at two elements associated with each other, then from the orientation of the surface vector you can get which direction it is pointing, whether it is a outward direction or inward direction, and then one element, if it is pointing outward, it would be positive. For example, this case the neighboring element it is taking inward, for this face it would be negative. So, if you go back to this example of 9 and then look at all this information, then you can see each of these element and you can rather explain each of these connecting faces individually. So, let us start with, as our convention of the local element, this was F1, locally F2, F3, F4, F5, F6. These are our local indexing. So, this theoretically should be face which is connected with the vector. So, F1 element which will have SF1, F2 will have SF2, F3 will have SF3, F4 will have SF4, F5 will have SF5, and F6 will have SF6. Okay. So, these are my local element or local indexing of the element that we have used as per our sign convention. So, now you look at the connections between element number 9. This is now we are in the global indexing framework. So, here the numbers that we get to see, these are global. Now, you look at 9 and element number 1. These are the two elements, they are connected with faces. Global face number is 11. Okay. So, 11 is common for both element 1 and element 9. Now, the local indexing is for these face connectivity elements. 1, 2 is the local indexing. So, the global indexing would be 1, 9. So, these are elements. Okay. So, this is how you maintain the system. Okay. That means for 2D cases, every 2D system, each element associated with these two elements, as we said, for when we consider element number 1, the surface vector is going outward. For element number 9, the surface vector at surface 11 is going inward. So, when it is going inward, it should be with negative sign of that surface vector. Now, for this surface vector, we maintain a global indexing of 1 and 2, which is sort of a universal for any 2D element associated with one space. 1 means the connecting global indexing which is here, which is the element 1 to element 9. So, this global indexing of the element is very important, because whenever we have assigned local indexing 1 and 2, 1 means surface vector would be positive sign, 2 means surface vector would be negative sign. So, this is the convention that, I mean, obviously it is up to the user how he translate these things in his programming, but this is typically the convention between two elements. When there is a connectivity and you map the connectivity, always you have a local connectivity, this is local and this is global elemental connectivity, this is local face connectivity. So, whenever it sees face 1, it will be multiplied with positive sign, that means it immediately points to the direction. So, the vector would be 1. For this particular case, if you look at it, as soon as we see 1 and the global indexing of the element is 1, so 1 connecting face is 11. So, both the elements has a common face number 11, which is a global number. So, when you go in the programming and look for the data structure, it finds that global indexing. As soon as it finds that global indexing of this face, it finds that a face number 11. So, it will fetch that information from the data structure. Face number 11 is connected with element number 1 and element number 9, and immediately it also picks up the information of local face numbering, that is 1 or 2. For element number 1, it will pick up 1, immediately it understands that the surface vector is in positive side, that means it would be pointing outward, which is currently shown here. And as soon as it picks element number 9 and the local surface indexing is 2, it will understand this would be minus sign. So, that means it would be inward as it is shown here. So, this is exactly what we are talking. So, that means every two element in two dimensional system, they are connected with a common face, and that face also has a local indexing like this 1 and 2. There will be global indexing to that. The face number is a one single face number which is globally indexed, that is face number 11, and the global element number which are associated with that global phase number is 1 and 9, and for them the local phase indexing is 1 and 2. Similarly, if you look at the other element, it would be much more clear, or you can visualize the system. Now, let us move to the next element, element number 9 and between element number 2. So, this is 9 and 2. So, global indexing of the phase is 10. So, as soon as it says, so I have a local phasing which is again 1 and 2, that means this is plus, this is minus, global element number which is 2, 9, common phase is 10. This is again global and this is phase number. So, whenever it picks the phase number 10, the immediately data structure it will find that it is connected with element number 9 and 2, and local phase numbering for element number 2 is 1, that means positive sign. So, this will be pointing outward. For element number 9 it will be local phase numbering 2, so this will be pointing inward. So, F1 and F2 they are of similar nature. Now, you come down to the other case where you see element number 9 and 10. Okay. So, when you come down there, the here 9 and 10 they are connected with a phase number 16. So, your again local phase numbering is 1 and 2 which is negative and positive, global element numbering is 9 and 10, and common phase for the global is 16. This is the phase number, this is global. So, as soon as you see that global phase number, it will fetch the information from your stored database. It is connected with global element number 9, global element number 10, and the local phase which is connected with the 1 is that 1 means positive, as it is shown here, the normal vector or surface vector is pointing outward, positive. For element number 10 it is 2, it would be negative, that means when we consider element number 10, the surface vector going inward. So, this is exactly what it does. So, similarly you come down to 9 and 11, the pattern is same. The global phase is 22, phase connectivity 1 and 2. So, 1 would be positive, 2 would be negative. Global element numbers is 9 and 10, and the common phase is 22. So, when you find out the common phase 22, it picks the global element number 9, it also picks the global element number 11, and the local phase connectivity 1 which is associated with 9, that means it is pointing outward as it is here, and for 11 it is negative. And then reverse, then you move to the other element 8 and 9, you come here 8 and 9, the global phase is 23, local phase connectivity 1 and 2, again positive, negative, and this is the number. So, based on the global phase number 23, it has the information of element number 8 and 9. For 8, local phase indexing is 1, that means it is positive. So, if you look at 8 here, things are going outward, so which is positive. For 9 it is 2, negative, that means it is coming inward. So, similarly it is between 6 and 9. So, that if you see this, it gives you an clear picture how you store these local and global information. So, this needs to keep track of not only the element numbers, face, node, local face indexing and so on. So that now that gives you an idea how involved a unstructured grid system, because this requires lot of data structure issues, because it has, I mean, you need to define element numbers, you need to define local element number, you need to have a connectivity between local element to a global element, you need to define phase number, you need to have local indexing of the phase number with sign convention. So, that actually takes into account the orientation. Then you need to have global phase, you need to have connectivity between local to global phase of a particular element and so on. So, completely if you see this whole business, this is how it looks like. This is really, in one way one can say it is really ugly, because this was not the case when you have compared the completely structured system. Structured system was much simpler to look. This is completely different ball game. Here it actually gives you an idea. These are random, there is no sequence, this is just for an example to show how mapping is done. Okay. So, this is the element 9 which we have been discussing and the surrounding element like this, but if you go back to just one other element like let us say 11 or 15, you see this is connected with this surroundings elements and they are vector, some of them going out, some of them coming in. So, that is true for the other things. This is how it is actually done. So, similarly like your structured system, if you put the algorithm in place, so how you find and do the calculation? First thing is that one, you declare the data structure, declare the gradient array and initialize. Okay. So, you can initialize to 0. So, you do that. So, you declare the gradient array and initialize. Number 2, second step, you loop over interior faces. Okay. And there what you need to look for, you compute the flux, compute flux equals to phi into SF. So, you go over all the interior faces, that means you first declare the gradient array, then loop over these interior faces. So, you go by these faces and then compute the flux. Once you compute the flux, then you add this flux to gradient of owner element and subtract flux to gradient of receiving element or neighbor element. Okay. So, that means you have gone over this loops, all the phases, you have done the calculation. So, this means you go over all the phases and third step, you loop over boundary faces. Okay. There again you compute flux equals to SF, again you add flux to gradient of owner element, then fourth step you loop over all the elements and divide gradient by the volume of element. Okay. So, the complete idea is that you define the data structure and essentially the data structure for the gradient array, initialize them, go over the faces and then you look for each faces here and compute the fluxes. So, that means I go to this phase, this phase, this phase, this phase and compute this flux. Now, when you compute the flux, then you for this you add to either this element is the owner element. So, you add to it, this is the neighbor element, so you subtract from it. So, that is where your local indexing comes into the place. Then you loop over all the element and then finally you do the same adding and finally you treat the boundary elements and divide by the volume to get the gradient. This is how you do for the unstructured case, and we stop it here and then look at the element in the subsequent lecture. Thank you.